Welcome, my friends. In this video, we will discuss the one-sample confidence interval for the population proportion. There are a few different angles to view what we are trying to estimate with the one-sample confidence interval for the population proportion. Some textbooks say that we are estimating the parameter p from the binomial distribution, which is true. But some intro stat classes don't cover the binomial distribution, and you don't have to know about the binomial distribution in order to understand the one-sample proportion confidence interval. My preferred approach is to think about the type of data that would indicate that you should be constructing a confidence interval for the population proportion. In a previous video, we found the confidence interval for the population mean, which was based on quantitative data. But if we have categorical data that is non-numerical, we can't really calculate the mean, so we need some other process. For example, say that from a sample of 100 GRCC students, 60 state that they believe in extraterrestrial life. The possible outcomes for this variable are yes or no, which is what makes the variable categorical. This is a point of confusion for some students. They look at the numbers up here, that there are 100 students and that 60 believe in extraterrestrial life, and think that we have quantitative data. But if you think of the response you would get from each individual, which are either yes or no, you see that the data itself is not quantitative, it's actually categorical. The most common way to summarize categorical data is to calculate the proportion of successes to the total sample size. We can calculate the proportion of GRCC students sampled who believe in extraterrestrial life by taking the number of successes, 60, and dividing by the total sample size, which is 100. We get 0.6 or 60% of students from the sample who believe in extraterrestrial life. You may or may not be familiar with the difference in the notation p versus p hat to represent a proportion. P is the population proportion, which makes it a parameter, as it is based on everyone in the entire population. This value is the proportion calculated based on a census of everyone in the population. P hat, on the other hand, is the sample proportion, which is a statistic as it is based on a sample. It is the proportion based on only some of the individuals in the population. In the real world, a census is typically unrealistic, meaning we can't calculate P exactly. Instead, we settle for p hat, which is a point estimate for p. That just means that our sample proportion, p hat, is our best estimate for the actual population proportion value, p. For example, we had a proportion of 0.6 or 60% of students that say that they believe in extraterrestrial life from our sample of GRCC students. This is a point estimate for the proportion of all GRCC students who believe in extraterrestrial life. We only have a sample of 100 students, but we can view our results as an estimate for the proportion based on all GRCC students. Since p hat is only based on a sample, we can expect it to be off by a little bit. The sample proportion most likely will not exactly match the population proportion. This is why we need to create a confidence interval centered around p hat. We will have a range of values to which we believe the true population proportion falls with some degree of confidence. Let's take a look at the formula. You may or may not know this, but every single confidence interval always contains a point estimate plus or minus some margin of error. Here's the confidence interval that we use for the population mean, mu. To estimate the population mean, we had to find the point estimate of x bar. The margin of error, the part that gets added and subtracted to the point estimate, is made up of two parts. We have the confidence level multiplier, which is a t-score from the t distribution, and then we also have the estimate for the standard error of x bar, which is s divided by the square root of n. The standard error is just a fancy way of stating the standard deviation of the value up front, the point estimate. The standard deviation of x bar, or approximately on average, how much we can view x bar to vary on each sample, is s over the square root of n, the standard error. The confidence interval for the population proportion looks like this, and has the same basic form as the confidence interval for the population mean. The point estimate is p hat, and the margin of error is now made up of the confidence level multiplier z from the z distribution, as well as the estimate for the standard error of the point estimate, which is the square root of p hat q hat over n. The standard error can be viewed as the average amount that p hat tends to vary on each sample, the same way that s over the square root of n was viewed as approximately how much x bar varied on each sample on average. Let's dive a little bit deeper into the formula. You are most likely familiar with most of these symbols, but let's just make sure. P hat is the sample proportion, which serves as our point estimate, and can be found by taking the number of successes, x, and dividing by the sample size, n. By number of successes, we just mean how many individuals have the characteristic that you are looking for, such as believing in extraterrestrial life. Z is the confidence level multiplier associated with the level of confidence, which can be found in a variety of ways. We will use the inverse norm function from the TI-84 calculator to calculate the z-score in this video. Q hat is equal to 1 minus p hat, and is the proportion of failures from the sample. I have discussed the central limit theorem in other videos, which you may or may not be familiar with. I discussed the central limit theorem as it applied to the sample mean x bar. The central limit theorem states that, for any probability distribution, the sampling distribution of the sample mean, x bar, will have a distribution that approaches the normal distribution as the sample size, n, increases. Generally, we need a sample size of at least 30. In other words, if we were to find a whole bunch of sample means and start to make a histogram out of them, the distribution of sample means will be approximately normal as long as the sample size is at least 30. Well, it turns out that the same idea applies to proportions. The central limit theorem for proportions states that for any probability distribution, the sampling distribution of the sample proportion, p hat, will have a distribution that approaches the normal distribution as the sample size, n, increases. Generally, we say that n times p and n times q should be at least 5, although some texts say that these values should be at least 10 or 15. Let's briefly discuss the assumptions of the one-sample proportion confidence interval. As is the case with every confidence interval, we must have a simple random sample. This means that everyone in the population must have an equal chance to be chosen as the first individual in the sample, and for the second individual in the sample, and so on. This is typically easier said than done, but nevertheless, this is an assumption that we have. This is often implied in problems, although it is sometimes explicitly stated. Secondly, the quantities n times p hat and n times q hat must both be at least 5. This ensures that the distribution of p hat will be approximately normal by the central limit theorem. Now, based on the previous slide, I stated that n times p and n times q, not n times p hat and n times q hat, should be at least 5. But of course, we don't know the actual values of p or q. They are population parameters that require a census to find exactly, so we must use the sample counterparts of p hat and q hat instead. Alright, let's look at an example. A group of students at Grand Rapids Community College were asked if they believe in intelligent life on other planets. Of the 100 students surveyed, 60 stated that they believe in extraterrestrial life. Create a 99% confidence interval for the proportion of GRCC students who believe in life on other planets. Now the first thing to do is to write out some of the information. 100 students were surveyed, so the sample size n is 100. The 60 that believe in extraterrestrial life is x, the number of successes. The sample proportion, p hat, is just x divided by n, and is equal to 60 divided by 100, or 0.6. The confidence level is 99%. We need to check if n times p hat and n times q hat are both at least 5. Remember that q hat is just 1 minus p hat. 1 minus 0.6 is 0.4. 100 times 0.6 is 60, and 100 times 0.4 is 40. Both values are at least 5, so the central limit theorem ensures that we can use the normal distribution to approximate the distribution of p hat. Now, as for any confidence interval, we should also be assuming that there was a random sample, and as I've stated in other videos, we can imply that that's the case in most circumstances, even if it isn't explicitly stated. Alright, here is the formula for the one-sample proportion confidence interval. The picture centers p hat in the middle with 99% or 0.99 of the probability in the center and 1% split into the two tails, or 0.005 in each tail, so that the total probability sums to 1. The lower and upper bounds of the confidence interval go at the boundaries of the shaded area. The z-score that we need for the formula corresponds to the positive z-score at the upper bound. To find the z-score on the TI-84 calculator, press second, vars, and then select inverse norm. The area is the area to the left of the specified z-score. In our case, the area to the left is 0.99 plus 0.005, which totals to 0.995, so we enter 0.995. we leave mu and sigma at 0 and 1 to specify that we are using the z-distribution, which has a mean of 0 and a standard deviation of 1. Press paste, and you will have this output. Match this output if you have a TI-83 calculator, 0.995, 0, 1. Press enter, and we will have the z-score of 2.576, which is our confidence level multiplier. Plugging into the formula, we have 0.6 plus or minus 2.576 times the square root of 0.6 times 0.4 divided by 100, which becomes two different terms, one for the addition part of the plus or minus sign and one for the subtraction part. We get 0.7262 when we add and 0.4738 when we subtract. These are the upper and lower bounds of our confidence interval. Since the formula is a tiny bit more involved, I figured I'd show you how to type it into the calculator. I have a TI-84 calculator here, but any scientific calculator should work similarly. Type 0.6 plus 2.576 times the square root of 0.6 times 0.4 divided by 100. After that, you might have to close the parentheses on some calculators. If we press enter, we get the upper bound of the confidence interval. The lower bound is just the same thing, but the plus sign needs to change to a minus sign. On this calculator, I can press second and then enter, which brings up my previous calculation. And then I can scroll back through to the left and change this plus sign to a minus sign. And when I press enter, we get the lower bound. Okay, all we have left is the conclusion. We are 99% confident that the interval between 47.38% and 72.62% contains the population proportion of Grand Rapids Community College students who believe in extraterrestrial life. I like to state my proportion conclusions in percentages, as they typically make more sense to the general public. And we are done. Alright, my friends, we have finished our discussion of one sample proportion confidence intervals. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.